Welcome, everybody. Today, I'm going to talk about toward a better deep learning. And you guys all know me. I'm at the university. I'm also at Amy, and I'm at Keen. My main job is at Keen Technologies, a startup, an AGI startup, sort of speak. And I'm also, I founded Open Mind Research Institute, which is coming along really well. We'll be announcing the first fellows very soon. This talk is, I call it, the subtitle is Rationale and a Vision. So it's going to be a view of how we can get a better deep learning. It isn't a complete algorithm. I mean, it's a very ambitious goal to improve on the existing gigantic field of deep learning. And it's almost arrogant to criticize it and talk about its limitations. But we're going to definitely do all that. So this work is new work, it's incomplete, but at the same time, it's building on a lot of other work that's already been done and in some cases has been published, and in other cases is in people's theses. So that work is like by Khurram, Javed, Arsalan Sharaf Nassab, Shabansh, Fernando, Parash, King Feng, Rupam's student, Mohammed Al-Sayed, and my good colleague, Joseph Modial. Okay, so to make sure I'm saying all the important things, I try to give a summary around the very first slide. So as I said, it's a rationale and a vision. The rationale is in blue, the vision is in green, for better deep learning. So I'll talk about what I mean by a better deep learning, and in particular how I'm going to focus on continual learning as opposed to the normal kind, which I'll define as transient learning. And then I'll talk about how deep learning doesn't work for the continual learning case. The better deep learning, there's a name I'm offering for it. It's dynamic deep learning. Okay? I just thought that up a couple days ago. We'll see how it works. But in a dynamic deep learning, the network is grown unit by unit, and then, of course, it does continual learning over time. The key idea is that you have a backbone. The backbone is stable. There's a fringe around the backbone. The fringe is more dynamic and exploratory. And as the fringe is trying to succeed, trying to be useful to the backbone. And if it succeeds, it becomes part of the backbone. So you need a bunch of new algorithms to do this, and I'll envision them here in the talk. And I think kind of a final comment would be there's still a lot more to do, but none of it seems too difficult. And so I think we should be positive and optimistic. Okay, so continual learning just means you learn all the time, and every moment is both a training and a test. In the regular kind of conventional deep learning is transient learning because you learn in a special training phase, and then ever after you don't learn, so you don't learn during normal operation. So this separation, I think, is very artificial between the training and the test. Transient learning is an artificial thing. All natural systems learn continually. And so I just want to say that, from my perspective, which is that continual learning is just the normal learning. It really shouldn't even have a special name. It's just the normal. Every animal, every person is doing continual learning and not the other, not transient learning. So deep learning, conventional deep learning is unsatisfactory. At least it's unsatisfactory for continual learning because, well, these are the standard reasons. You lose plasticity. Over time, the networks lose their ability to learn new things. They can forget catastrophically. When they do learn something, they forget old things, and they do that much more than they need to. In fact, they preferentially forget the most important things they've learned in the past. You can also see policy collapse in reinforcement learning. If you have a deep reinforcement learning agent, their performance will often degenerate dramatically if you keep running them. They kind of solve the problem, and then if you keep running, they collapse. It's kind of odd. This has been shown, both the loss of plasticity and policy collapse have been shown here by Shabansh and Fernando and others. And yeah, those are about to appear in a major publication in the next couple of weeks. And generally speaking, deep learning is slow and brittle. All of the examples in the training set, they must be repeatedly presented in an uncorrelated way. If you don't do it just right, you can get this forgetting or loss of plasticity. So let me just stop with that. I think it's enough. So what we learn is that backpropagation, deep learning, as it's normally done, is not enough. We have to free our minds to think differently. Now, this is my sort of my pep talk slide. Now we are, it's 2024, deep learning is ascendant, but we can still think again because for what agents need, for what we need in reinforcement learning, deep learning just doesn't work well. So we should let it go. We should relax and be brave and think differently. So, are you ready to think differently? Let's freaking go. So, first I want to distinguish, or just acknowledge that conventional deep learning networks, they have this fixed designed structure, like this layered structure, or a layered structure with particular roles in each part. It's all designed in advance. Whereas I want to think about a more organic system. The dynamic deep learning networks, they're accumulated unit by unit, and so we have a sort of flexible, maximally flexible, a grown structure. So here are some networks that Curram has worked with, and they're actually grown. So this is the same network as it's growing from just a single output node with many inputs to introducing intermediate units, sort of feature units. And then by adding more and more of those, you get a large network that is multi-layered. And so I think that's the way we want to go with dynamic deep learning. And I'm not going to give a specific algorithm for how the network is grown, but I'll assume that it is grown, and we can think together exactly how that should be done. Okay, so here's the first big step. The first and most important step is to distinguish the part of the network that has already been learned from the rest of the network. So this part that has already been learned, I'm going to call the backbone. So here's a picture of a network I drew on my board, and the blue ones are meant to be sort of useless units, and the black ones are the backbone. And we know that a full deep learned network has many dead units, units that don't contribute to the function, they're unused. Shivansh and Fernando have shown this in their work with continual backprop, that many times even more than half the units can be dead by the end of learning. So let's prune those away, and then we have just the backbone. And let's think about this some more. So the backbone is the part of the network that's already been learned. If you want to think about knowledge, it's the knowledge that has been obtained. And it should be preserved and protected. As you go on to learn new things, you shouldn't dismantle what you have already learned. And unfortunately, deep learning does do that. Okay, but anyway, it shouldn't be done. We should have a backbone. We should rely on it. We should accumulate it and learn more and more. So let's think about this. Be more specific. I'll think of these as ReLU units, which means they may have a weighted sum, and then there's an activation function that's applied to the weighted sum to produce each unit's value. So the unit's values are the x's, and the weights are the w's. So here, for example, we would multiply the input, whatever these inputs are, maybe they're binary ones and zeros, and we multiply them, and we get a sum here, and then we apply the activation function. The activation function for a ReLU is if the sum is greater than 0, then the sum is the output, and if it's less than 0, then the output is 0. So here I'm showing a particular flow of activity through the network. We're seeing an input of 1, 0, 1, and that propagates through just approximately according to this idea. We do a weighted sum, and then we see if it's greater than 0, and if it's greater than 0, then that's the output. So the number shown within the node is the output of the node. Well, I'm hopeful that some of you can see the numbers. Can you tell what color the numbers are? If they're green, then they can see them a little bit. You know, the particular values are maybe not so critical, although I will talk about them later, and I'm sorry if they're hard to see. So we're flowing through, And now we have the rest of the network, which is not the backbone, which I'm going to call the fringe. The fringe is this more exploratory, more dynamic thing that's moving around and tries to come up with things that are useful to the backbone. And if they become useful to the backbone, then the backbone will listen to them, and then they will become part of the function, and so they will have joined the backbone. So I imagine it as there are many, the number of fringe units is probably bigger than the number of backbone units, certainly at the beginning. And I'm only showing a couple of them. So you want to notice from this example that the output connection, so I'm going to use certain words. One, if we take a network, take a unit like this one, I will talk about its input weights, and these are its input weights. And its output weights, this one only has one output weight. It's a 3. Okay, so input weights, output weights, every unit. And so the fringe units will typically, but not necessarily, they will typically have an output weight of 0 because they don't affect the behavior of the system, right? And so they by definition, that's what it means for them to be on the fringe. So they don't affect the system, so the weights from them to the backbone must be 0. But these weights can learn. The backbone could choose to make this weight larger, and then they would if they have a useful feature that they've formed. Okay, so that's the general idea. The fringe consists of these units that are almost on the backbone, and the goal is to join the backbone, and we're going to grow the backbone in this way. So to speak a little further, we can have a target, because this is just regular supervised learning. And so here I'm showing a case where the target coming back to the output node is 5, which is bigger than the activity, which is 3, so there's a positive error. The error is the difference between the target and the actual output. I'm going to write E of t for that target, so you might want to think the loss is the square of E of t. And so then the gradients would be this form. Actually, gradients is a little bit of a misnomer. The gradient is actually the vector of all the partial derivatives, but it's conventional to talk about the gradients all over. Like the gradient of this weight is this partial derivative. Okay, so those are the gradients, and I also want to talk about the gradients of the squared error with respect to the unit's activities. Okay, so this. And these are a different thing, and I want to call them hungers. I'm going to call them hungers. The idea is that the backbone has learned as best as it can with its own structure, and it learns by reducing the errors, by reducing the hungers, and there will be a residual. There will be certain hungers that it doesn't have the resources, doesn't have the signals, the features, and can't be reduced to 0. Of course, if they are all reduced to 0, then we're done. But if normally there will be things that can't be reduced to 0, and so they will hunger for new features that enable them to do better. And so I speak of it as a hunger because the hungers here are at the last node as a positive hunger because the target is greater than the output. And this node here has a negative hunger because, it's because of this negative weight. And in order to make this guy higher, this guy wants to be lower, or he doesn't want to be active. Okay, so think about this. Think about what's going to happen to the network as it lives its life. I'm showing here an instantaneous snapshot of what one particular input and one particular output and all the values in between, and there's some errors. Next time step, there'll be another example, another target, there'll be a different set of errors, and all these errors or hungers will be things that we want to reduce, and we're trying to find fringe units that provide features that enable them to be reduced. Oh yeah, I added these so that we could talk about the nodes, or if you wanted to ask me a question about a node, you could just refer to the node names, A through G. But I hope you got the idea. Because the idea is, with this design, we need multiple new algorithms. We need to learn within the backbone, we need to learn within the fringe, we need to find the backbone, we need to maintain the boundary. So let's just talk briefly about those things and think it through in our heads. Learning within the backbone. Well, that's going to be, it can be normal backprop. And it can be, you want to mix it with step size optimization. Because remember, we want to protect the backbone. The backbone is our knowledge. And so we don't want to make large changes. We want to move slowly. And step size optimization will do that. It will learn that the step sizes should be small within the backbone. How about learning within the fringe? Now that's a really challenge because we can't use backprop within the fringe. Why not? In backprop, you move the weights according to the gradients, the gradient of the error with respect to the weights. Say again? If you look at by definition, the gradients for the fringe weights are all zero. Because by definition, the fringe doesn't affect the output. So it does not affect the error. And so all the gradients are zero. So we have to do something else. Isn't it strange that our standard algorithm, we can just immediately see it can't find new features out of nothing. So how are we going to do that? Well, I'm going to tell you how we're going to do that. That's going to be something I call shadow weights. And then we're going to find the backbone. So how are we going to find the backbone? Can you guys just think, how are you going to find the portion of the network which is having which matters, which affects the output of the network, and distinguish it from the part of the network which does not affect the output? How are we going to find the backbone?
This satisfies a hunger.
Say some more.
So in your previous slide, you're showing there are hungers where certain nodes want to see larger or smaller values, and maybe if the backbone can satisfy those needs.
But how are we going to find which units are on the backbone? So, by definition, the output unit is on the backbone because the output unit does the output, and the output is the response of the system. Was there an idea in the back?
Would you just trade a full network and then look at all the units that are dead?
It's something we want to be ongoing, but so how do we find the dead units? How do we find the part that's still alive and is affecting Farzana?
There is small perturbation in the weights in the backbone affects big like changes in the output. We know that these are the effective weights for part of the backbone. So just adding some small noises randomly to.
So are you suggesting we do a slight perturbation to the weights and see if they affect the output?
Yes.
I guess that would work. I think there are several possible ideas. That's our first one. Do you have another one?
If you want to do it continually, you can track the average gradients of each of your weights. If they're like non-zero fringe.
Okay, so if we're at equilibrium, the average gradient of everything will be zero, right? Because things have gone up and down, they've reached equilibrium. So you can't take the average of the gradients. But the gradients if the gradients are non-zero, then that means that weight had an effect on that time step. And so it had an effect. So if you just look at like the square of the gradient, and average the square of the gradient, you'll find the backbone. I think that's the simplest idea, it relies on backprop, because backprop is the way you compute the gradients. If you did the backprop, you would get the gradients everywhere, and you could just see if they're non-zero. Another idea, Farzana?
I guess I disagree that this is a good way. Because, like, imagine you're in continual learning and you're seeing similar samples for a period of time. So, like, the network will converge at some point where the gradient would be zero, but you cannot, like, you see gradient is zero, but some part of the network is still backbone. So, like, having gradient of non-zero is not necessarily resulting in understanding what the backbone is, but if you add this perturbation and you see the large effect in the output, you are certain at any time that this is the backbone.
I think that's valid. All that's valid. Different, but just before we go on, I want to mention a third way, which is, you know, the output units are on the backbone, and you know, if you think about it, if some other unit has a positive weight onto the output unit, then that one also, a positive or a negative, a non-zero weight onto the output unit, then that preceding unit has to also be on the backbone. And I like this because, well, and then there's like a closure property, right? If that preceding one, if he's on the backbone, then anybody that he uses is also on the backbone. And it sort of propagates backward. It's not like backprop, though, because this is a propagation just based on the values of the weights, whereas backprop relies on the instantaneous activity values. So this kind of slow propagation backward that just depends on the values of the weights it has many implementation advantages over backprop. In the circumstances when you can't do backprop, you could still do this slow propagation of utility. And this is what I'm going to recommend. But let me go ahead now. Yeah, this is the next thing, actually. So I'm going to talk about utility. So utility is something that you've heard about before. Shibansh and Fernando talk about it. They use it in continual backprop. And so we're going to define units that have a non-trivial amount of utility are defined to be on the backbone. And then, of course, the output units are going to be on the backbone. So we're going to place a unit of utility at each one of the output units. This is where the backbone starts. And then every backbone unit that has utility will pass a portion of it back to the preceding units that have non-zero weights onto it. These are the weights that it uses. And important here is that utility is conserved. If you pass utility back to one of your predecessors, you lose that utility, and there's only so much of it. And if your utility falls below a threshold, then you're no longer on the backbone. Well, this is an outline of what a utility propagation algorithm might look like. Now, let's talk about the biggest question mark, how the learning works within the fringe. So let me do it first in words, and then I'll do it in pictures. So by definition, as we talked about, the gradients of the fringe weight, so this gradient, they're all always zero, and so we can't use backprop. So instead, each fringe unit is going to have a master unit on the backbone that it is going to try to get to listen to it. So the master will be the unit on the backbone that the fringe unit hopes to serve, hopes to provide utility to, hopes to provide value to, and thus gain utility from the master. Okay, so now note that by design, the weight of a fringe unit onto its master must be tiny. It must be zero or tiny, because if it had a large weight onto the master, then it would interfere with the master. It would interfere with the backbone, and it would interfere with what has already been learned, and I guess it would even then be on the backbone. So when you, by definition and design, each fringe unit will have a zero or tiny weight onto the backbone, and that weight will have a small step size, because even if you had a 0 weight, if you had a large step size, you'd quickly gain a large weight, and you'd interfere with the backbone, interfere with what has already been learned. So the weight on the fringe unit onto the master, onto its master, is 0, but the fringe unit nevertheless aspires to grow its master weight, the weight onto the master, and thereby join the backbone. So to do this, it has what I call a shadow weight, a plus or minus 1 shadow weight onto the master. So the setup here is that only the master can change the real weight, because it might, some of the error or hunger that it feels, it sees, but of course the fringe unit can set its shadow weight arbitrarily. So let's actually skip over this one and go to the pictures now. So here is the situation we were looking at before, but now I want you to think about D and E. These two units are being added at this moment. We call it imprinting. The moment of creation of a fringe unit is called an imprinting process. So we imprint. When you imprint, well, you're assigned a master. So here, unit E, here are the master units. E's master is C, D's master is B. And so you've been assigned a master, and then you're assigned a shadow weight. So here's the shadow weight. This weight, like I said, shadows the real weight. And if you recall, well, it's written here, the hunger at unit C is positive, so the shadow weight is assigned a +1. And then the hunger is negative at B, and so we get a -1 shadow weight. Oh, there should be one more step. Well, I guess I can just say it. When we add these, when we imprint D and E, we add in their connections, their input connections. Here, the input connections I've just chosen to be. They could be chosen in many ways. You might imagine they're chosen at random from the units that precede the unit that we're adding, that precede the master, in order to retain a feed-forward structure. So here, unit D is connected to A and to an input, and E is connected to B and an input. And then the weights of the fringe unit, those are imprinted, which means they are taken from the input pattern at the time of creation. Now, the easiest way to understand this is that it's like you set your shadow weight, and then, so here we have the shadow weight, and then you replay the example. When we replay the example, there's a positive hunger, and so if the shadow weight was real, the errors would propagate, the gradients would propagate back to E, and E would adjust its weights, and the way it adjusts its weights, that's what happens in imprinting. So here, this is a +1. We have the gradient passed back. There's a positive. We want to increase the value of this node, so we make where we have a 1 input, we make a positive weight. Where we have a 0 input, we make a negative weight. And in this case, the hunger is negative. The shadow weight is negative, so we want to push this guy down. So, oh no. We don't want to push this guy down. Even though the shadow weight is negative, you still want this unit to come on now so that he can have his negative effect on B. So still, we increase the weight to the positive things, and we have negative weights for the inputs that are 0. Okay, so that's how we imprint a fringe unit and aspirationally connect them to the backbone. The shadow weights are their aspiration about how they'd like to be connected. Okay, so that's the vision. And the last thing, I just want to remind you about the step size optimization is an integral part of this. Controlling the step sizes prevents catastrophic forgetting, protects the backbone from the more dynamic fringe. So what happens is the fringe units create a shadow weight, they have this connection to the master, and if what the fringe offers to the backbone is something that the backbone finds useful, then what will happen is that the weight to the master will increase its step size first, and then once its step size is non-trivial, then the weight will increase and it will join the backbone. Okay, that's the picture. That's the vision for a better deep learning, most suited for continual learning as opposed to transient learning. This is a kind of deep learning that's dynamic because, well, we're learning all the time, but moreover, we are changing the structure all the time. The basic idea is that the backbone is stable, the fringe is dynamic and exploratory. As the fringe succeeds, it becomes part of the backbone. The idea is shadow weights are key to that. And other new algorithms are needed, and we've envisioned them today. So obviously there's much more to do. There are parts that have been left out and parts that are not completely specified. But to me, at least, none of it seems particularly difficult. I think we can actually make a better deep learning that's more suited for agents and reinforcement learning. Thank you very much.